Yes, welcome all at our weekly seminar at Jagiellonian. Today, our speaker is Rose McCarty. So Rose is now at the Warsaw University, being a postdoc over there for
Yes,
for what? For
6 months.
For 6
That's
months.
right.
And you graduated at Waterloo last year.
Yep.
Last year, and your main research interest lies in structural graph theory. Are you a mathematician or more a computer scientist?
It's a tough question to ask me on the spot. I wasn't prepared for this,
Okay.
but I have to still go with
Let's leave it undefined. Yes.
Okay.
We're very glad that you came here. We're looking for a week or more than a week of research, and the floor is yours today.
Thank you. Yeah, thank you for the invitation. So I'm going to be talking about this circuit decompositions of group labeled graphs. And this is joint work with Jim Gielen, who was my PhD supervisor, as well as Paul Wallen. And this is part of an ongoing project on vertex minors, but today I'm not even going to say what vertex minors are, and definitely not how they relate, because I want to really focus on what the actual problem is here today that we've answered. So here I've drawn a group labeled graph. And a group labeled graph is just a directed graph where each arc is labeled in a group. And I'm allowing loops and multiple edges as well. And so here the group is Z. And in general, I'm going to write the groups additively. So let me be a little bit more careful about what a group labeled graph is. So a group labeled graph is a tuple where G is this directed graph and gamma is a labeling from its arc sets to some group, which I'll usually call capital gamma, but here it's just Z. And also I'm going to call the arc set of G sometimes just the edge set or E of G. So I'm just going to use the word edge to refer to arc sometimes because it's a bit easier this way. So we're looking at circuit decompositions, and in order to say anything about circuit decompositions, I'm going to need my graph to be Eulerian. And so all graphs in the talk are Eulerian, so I don't have to say this again and again. And what that means is that each vertex has even degree in the undirected sense. And also that the underlying undirected graph is connected. So whenever I say that a graph is Eulerian, here it means that the undirected graph is Eulerian. And now I'm interested in circuit decomposition. So let me also say what circuits are. So for circuits, I can start at some vertex. So here I'll start at this vertex V, and then I can begin moving along arcs in either the forwards or the backwards direction. And no arc can be used twice. I'm going to have to come back to where I started. So I can use, say, first this arc is labeled as 1, and then the backwards direction I might walk along this arc, and then around the loop. This is fine, and so on. Right, so I'm thinking of circuits as being closed walks without repeated arcs. Okay, so there's in graph theory, sometimes you take different definitions for circuits, and this is the one that I'm working with. So I'm allowed to traverse arcs in either the forwards or the backwards direction. And whenever I traverse a loop, I also have to specify whether I'm traversing it in the forwards or the backwards direction. So it would be a different circuit if I went around with the orientation of the loop versus if I went around the wrong way. And I'll call it B circuit if it begins and ends at B. So the whole point about group labeled graphs is that they encode the weights of circuits. So if I'm given a circuit, I can tally up each group element that I see in order where an arc contributes its inverse if it's traversed in the backwards direction. So for this circuit, the word that I get over the group is 1 plus -3 because that's in the backwards direction, plus 2 if I go around the loop in its own direction, plus 3 minus 1 because that's again a backwards edge. And note that this definition doesn't matter. It doesn't matter that the group's abelian. So I actually have an order on the arcs, and that's the order in which I'm tallying everything. So I'm writing groups additively, but it's kind of for historical reasons. I don't actually care that the group is abelian. What I do care about, though, is the group element that this word evaluates to, and that's called the weight of a circuit. So here it's 1 minus 3 is -2, plus 2 is 0, plus 3 minus 1 is 2. And so this is the weight of the circuits. And it's denoted by gamma of C. Yeah, so this is why group labeled graphs were originally introduced. You can find some matroids that correspond to group labeled graphs based off of which circuits have non-zero weights and which have weight 0. So we're going to care about which circuits are non-zero. The circuit is non-zero, its weight is non-zero. Okay, so I've finally, I think, prepared all of the actual definitions on group labeled graphs and their circuits. I'm about to move on and say what our problem is. So I wanted to stop first and ask if there are any questions about just the setup that we're dealing with so far. Okay, I see a couple of shakes, so I'm going to take that as a good sign that there aren't any questions. So the title of the talk is about circuit decompositions. I'm actually going to look at circuit decompositions where each circuit begins and ends at this fixed vertex V that I care about. So circuit decomposition says to take your original graph and to find a collection of circuits which decompose its edge sets. So the way I like to think about this is that I have my group label graph. And I'm writing it as a sum of circuits. Maybe I'll use this one that I had already started with before. And then in this case, what remains is still a circuit. And so that's one example of a circuit decomposition. Right, so something like this. And I'm interested in circuit decompositions where each circuit begins and ends at a fixed vertex V. So V circuit decomposition is a collection of V circuits which partitions the arc sets. And now the question that I care about is what is the maximum number of non-zero circuits in a V circuit decomposition? So the way that you can think about this.
Rose, where is this triangle in the?
Oh, I hope it's here. I forgot to write.
Okay, yeah, oh yeah, sure.
On the original. Okay. Yeah, thank you. Good.
Should be fine.
All right. Yeah, so the way that I like to think about
And the
V
arrow,
circuit.
oh, the two arrows.
So
Okay.
let's see.
Yes, it's okay. Sorry.
That's right. Yeah, let's check. Cool. Yeah, so the way I like to think about B circuit decompositions is that I'm finding an Eulerian circuit and I'm cutting it in a few places whenever I get back to B. So the Eulerian circuit says start at B, follow this circuit, and then once I get back, go to the next one, and so on. And so I am cutting an Eulerian circuit at B into so that as many parts as possible have non-zero weights. That's the problem. So another way of saying that is, what is the maximum number of non-zero circuits in a B circuit decomposition? Let me say something about the reason why this came up in our research, and it's going to be a really kind of vague statement because it's hard to go into all the details in this length of a talk. But there's a proof by Bert Gerards which gives you the forbidden minors for matroid being graphic. And the way that that proof works is by looking at sign graphs, so group labeled graphs where the group is just C2. And we have a project which is analogous to this. You can think at least of the motivation for this as being related to matroids, but for symmetric matrices, where the same set indices the rows and the columns of the matrix. And so this is where graphs come up because we're looking at basically the adjacency matrix of a graph instead of its incidence matrix. And for us, we care about group labeled graphs where the group is Z2 with K. But it turns out that our proof works for general groups. And so we've written it up this way to make it just more general. So this is where the question comes from. And the result that I'm talking about today is that we have a really precise answer to this. We can tell you what the answer is. And since it's the theoretical computer science seminar and give a question at the beginning, I'll say that we're pretty sure that you can transform this into an algorithm. So in particular, we believe that as long as you can solve the word problem for the group in polynomial time, that then you can answer this question in polynomial time. So I'm not going to write that on the board because we're still checking some of the details of the algorithmic part, but that's how it should work. And the word problem, by the way, would just say, given a word over the group, can you tell in polynomial time whether or not that word evaluates to 0? Okay, so it's going to take me basically the whole talk to tell you what the answer to this question is because the truth is complicated. So this is kind of unfortunate. I think that the theorem is really pretty because it's exact, but the truth is unfortunately maybe not so pretty. So let me look at a special case of this first, and that is when is this number equal to 0? So it's going to be helpful for me to give this maximum number a name. We so far are calling it the flooding number. And the reason why is kind of due to a historical anachronism, which was how we were thinking about this problem. So what's going on is that if these circuits weren't decomposing the arc set, but were instead just edge disjoints, then the answer to this question is already known. And so we originally wanted to approach this problem by finding a maximum collection of edge disjoints, non-zero circuits, and then trying to add more and more edges of the graph to that collection. And so we were thinking of this process as being flooding our collection to the rest of the graph. But we realized that that's just not the right way to think about this. But still, so if anyone has a better name, please let me know. And the notation is going to be nu tilde of G and gamma. So nu like the matching number because this is kind of similar, and the tilde is supposed to look like a wave for flooding. So I'll have to just go with it for that one, but I want a phrase to use for this number, so that's what I'll call it. Yeah, okay, so let's look at this special case, which is just when is this number equal to 0? And I'm going to start by writing some examples of graphs where this number is equal to 0. And then I'll write the proposition, which says that those are essentially the only things that can happen. So one rather simple reason is if every arc in the graph just has weight 0 to begin with. Like this. Then certainly there's no circuit of non-zero weights. And so I certainly can't decompose my graph into more than into a circuit decomposition where at least one of the circuits is non-zero. Yeah, so this is a really simple reason. But let's look at a slightly more complicated but similar case. So I'm going to change the labels incident to this vertex by making this one have weight -1 and all of the others have weight 1. And now let's look at what the possible weight of a V circuit can be. So I start at V, I walk around for a bit. At some point I enter this vertex, and I have to do it by something of weight -1, yeah? And then once I leave, I have to leave with weight 1. And so there's a nice way of saying that this group label graph is actually equivalent to this one. And this will work in general. So what I can do is I can take a node U, which is not equal to V, and I can take a group element and I can use it to change the weights of the arcs incident to U. And this operation is called shifting. So shifting at U by alpha is the following. I'll say what it does to arcs going into U and loops and arcs going out of U. So for each arc going into U, I'm going to subtract alpha from the right-hand side. So this includes it loops. And then for each arc going out of U, I'm going to add alpha to the left-hand side. And I'm being careful about which side I'm working with because I didn't require that the group was abelian. So now you can see that this doesn't change the non-zero circuits because whenever I enter in, I have to then leave through something which cancels out this minus alpha. And in general, what it does to the weights of circuits is the same thing that it does to loops, which is that it conjugates the weights of circuits. So it actually doesn't change the order of any circuit. And I'm allowed to repeat this operation as much as I want to any vertex other than B. In fact, I could even do it at B. It still wouldn't change the non-zero circuits, but it's just kind of easier to not do it at B. And I can also do it by any group elements. So shifting in my labeling, any new labeling that can be obtained this way. And so now I can go back to my examples, and so far I really only have one reason, which is that either my labeling was zero labeling, or a shifting one for zero labeling. So far, nothing really interesting has happened. I've just said, well, maybe I don't have any non-zero circuits to begin with. And so the fact that I'm looking for a decomposition into non-zero circuits hasn't really showed up yet. But that's going to happen with the third example. So I'm going to draw a particular graph. Here's my vertex B. This graph is going to be labeled over Z2 to 2. And it looks like this. And so now, since every element is order 2, it doesn't matter in which direction I traverse an arc, it's going to contribute the same thing anyways. And it also doesn't matter which order I traverse the arcs in. All that matters is that I have to traverse all of the arcs since my circuit decomposition decomposes the arcs. And so what's the only possible weight of circuits? It's just the sum of these 3 elements, which is 0. So even though there's a non-zero circuit, there's no non-zero B circuit which uses every edge. And now it turns out that these are the only things that can go wrong. So I can combine these steps in a certain way, but no really new ingredients are going to appear. So let me say how to combine the steps. So if I have a set of vertices of the graph, which doesn't contain V, so there are exactly 2 infinite edges to that set of vertices V, then it might look like this, and that maybe there's a unique way of going through this 2 edge cuts. And so let's say when that happens, first I'll call this set of vertices a 2 edge cuts. So I'm thinking of a 2 edge cut as being a set of vertices which doesn't contain V and which has exactly 2 edges in its boundary. And now I'll say that it's well behaved if the labels of all of the edges of both ends in here generates a group that's isomorphic to Z2 to the K. And that's what I figure out. So it's well behaved if the group generated by labels of all of the arcs with both ends in that set, which I'll denote by this, E of X. It's also morphic to Z2 to the K for some K. And so if all of the labels of edges of both ends in this set, if they generate a group that's isomorphic to Z2 to the K, then since I have to use all of these edges, as soon as I enter into set X, right, I have to use all of these edges and then leave. And it doesn't matter what order I use these edges in, because the group's abelian, and it doesn't matter whether I traverse an arc in one direction or the other direction, because everything has order 2. And so that means that the contribution of this guy, if this arc is oriented up and has weight beta 1, and this arc is oriented down and has weight beta 2, then the only way I can go from this vertex to this vertex through the sets is by an arc of weights beta 1 plus the sum of the weights of the things with both ends X plus then beta 2. So the claim here is that the flooding number of this graph is equal to the flooding number of this graph. And it doesn't matter that I oriented this arc up and this arc down. I can always flip the order of an arc by inverting its label, and that doesn't change anything else that I've talked about so far. Right, so let me say again what's going on. If I can write my graph as a sum of these circuits of given weights, then I can also write this graph as some of these circuits of the same weights, because one of these guys has to go through the 2-edge cut. So in this picture, I've got this 2-edge cut and this guy goes through it. So I'm giving you a hard job to go back and forth. Yeah, be a bit more consistent. Okay, so I'm going to call this operation decomposing on the 2-edge cuts. All this. So now I can state the theorem, which is that if the flooding number is equal to 0, if you can't write your graph like this, where at least one of the circuits has non-zero weights, then it's because there's a shifting, so that after decomposing on well-behaved 2-edge cuts, every arc is weight 0. Right, so it says after doing this operation, but don't change the flooding number, there's a really, really good reason why there are no non-zero circuits at all. So the formal statement I'm giving is that the flooding number is equal to 0 if and only if there exists a shifting gamma prime of gamma, such that all non-zero arcs, that's of this shifted graph, gamma prime, can be removed by decomposing on well-behaved 2-edge cuts. And I want to point out that there's really a unique way of decomposing on 2-edge cuts. So it doesn't actually, I said can be removed, but in fact, there's only one way to decompose on all of the 2-edge cuts, and it doesn't matter in which order you decompose on them or any of that stuff. Okay, so what I really like about this, and even though it's only a special case of the theorem so far, is that you can already see why it matters that the graph is Eulerian. Right, in order to do this decomposing step, we needed to know that every arc in here was used. And what's more, you actually see something about the group. So there are other theorems in this area that give you min-max theorems for different types of parameters that are analogous to this, but in none of them, the group really matters. I can't think of another example. And so here you actually see that the group matters. Okay, so let me give an idea of how to approach this special case, and then I'll say something about the general case. So you might ask, when is there no shifting which makes a 2-edge cut well behaved? And now the fact that shifting doesn't change the order of any circuits is going to come up. So if there was a circuit in X which had weights of order bigger than 2, then it certainly can't be well behaved, because no matter how I shift, I'm going to have this element whose order is bigger than 2. And it turns out that that's the only thing that can happen, at least when the 2-edge cut is minimal, is pushed as far away from V as possible. And in fact, it's a little better than that. So instead of just finding a circuit that was contained in X, we're going to say a little bit more, which is that I can find a trail that starts outside of X, goes immediately into X, uses every arc with at least one end in X, and has this special circuit as a subcircuit. Right, so the point is that I'm finding a trail which begins and ends outside of this set, uses precisely the set of arcs with at least one end in X, and has this as a subcircuit. So I'm really going through things in this order. Yes, this is better than just finding a circuit contained in X. Yeah, so let me write this definition. I'm going to give this an actual name. So I'll say that an X circuit, circuit C, that's supposed to be this one, C, such that there exist trails T1 and T2. T1 is this one that goes in, T2 is this one that goes out. So that if I compose everything, if I look at the walk where I go along T1 first, and then C, and then T2. So first of all, I can actually compose this, and this is actually a walk. Or trail, even if it doesn't use any arc more than once. And arc set should be precisely the set of arcs incident to at least one end, with at least one end in X. So the formal definition is that an X circuit is a circuit C, so there exists trails T1 and T2. So whenever I compose everything, I get a trail that has precisely the arcs with at least one end in X. But this, I think, is a better picture. Yeah.
So do we require that this is a 2H cut?
Yes, 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 yeah. I should say. Or S 2H cut. And now I can state a lemma which lets us deal with 2H cuts that are minimal. That is, that our push as far away from V as possible. And this will tell me whether or not I can find a shifting which makes the 2H cut well behaved. And so I would say that this is the hardest part of the proof. There's still more things to put together for this after proving this lemma, but this lemma is really where all the interesting things are going on. So lemma is going to be applied to a minimal 2H cut. Meaning there's no 2H cut properly contained in X. It's going to say that exactly under the following rules. So either I have a good reason for why no shifting will make X well behaved, and it's what I said earlier, that there exists an X circuit whose weight has order bigger than 2, or I'm actually going to have the 2H cut as well behaved. So either there exists X circuit C with its weight of order bigger than 2. That's my first outcome. And my second outcome is going to be that there exists a shifting which makes the 2H cut well behaved. That is, so that the subgroup generated by the arcs with both ends in X is isomorphic to Z2 to the K. But I'm actually going to prove something a little stronger, and this is where the key point comes in, and this is something that we keep on using throughout the whole proof of the general theorem, which is not only does the subgroup generated by all of these arcs here, not only is that isomorphic to Z2 to the K, but also for every edge here, if I look at the weights of the X circuits containing it, it generates the same group. Yeah, so what I like to think about this as saying informally is that I've got all this parity lying around, the Z2 to the K and its generators, and I can move that parity wherever I want within this set. If I want to find certain circuit containing this particular edge, then I can do that. And this is like really what makes the proof go through, and it shows up again and again in our proofs. So the first part is just going to say that there exists a shifting which makes the set well behaved. And the second part is going to say that for each edge, the weights of the X circuits containing that edge generate this same exact group. Okay, so that just says what I just said out loud. So either I have a good reason for why no shifting can make the 2-edge cut well behaved, or not only is there shifting which makes it well behaved, but also for each edge, the weights of the X circuits also generate that whole group. And this is somehow really key, not just to this part of the lemma, but to our whole proof. This idea that you can move the parity around freely. So I'm going to try and just convince you this is a good approach. I'm not going to say anything precisely about the lemma, but I want you to have an idea of how you'd approach proving this key lemma. And for that, I need another lemma of Lavas, which I think actually maybe just appeared in the Alon Spencer book. I forget where it appeared. It was only in a textbook, I think, as an exercise. But it's quite a well-known lemma. And the lemma is usually stated by saying that if you have a 4-edge connected graph, then you can find 2 incident edges to combine, which keeps the graph being 4-edge connected. This is essentially the same as dealing with minimal 2-edge cuts. And I'm going to state it this way. So I'm also only going to state it a little informally. So the lemma says that if I have a minimal 2-edge cut, and I look at a vertex in it, which is incident to an edge going outside, call it U, say, then I can find another vertex W1 incident to U, which is also inside this set. So that when I combine the UW1 edge with the UW2 edge, then what I get is essentially a minimal 2-edge cut still. Now, this word essentially is always scary to see in a talk. So what does essentially mean here? Essentially means that U could be a degree 2 vertex. Other than that, there's no 2-edge cut contained in X. So it's not that bad, but essentially I don't want to deal with it. If you have a degree 2 vertex, there's no reason you should have it for this problem. So you can always just smooth it. And it doesn't change anything. So you should just forget about it for this thought. Okay. So what's now nice about this setup and the lemma is that we can apply induction on the number of arcs of both ends in X, because I've removed this arc UW1 from X. Yeah, so I can do an inductive proof of the lemma, and it tells me that either outcome 1 or outcome 2 occurs on this graph. And now if outcome 1 occurs, if I get this trail that goes through precisely all of X and has a subcircuit whose weight is ordered bigger than 2, right? This is outcome 1. Then it also implies outcome 1 for the original graph, because I just follow the same sequence. It doesn't make a difference. All I've done is add this, right? So for trails, it doesn't matter. I again get over here the same thing. Right, the only thing that could have happened is that this first edge, this W2, W1 edge, could now go first through U and then to W1. Yeah, so here it might look like this, but I don't care. It's still trail like I wanted. So then if outcome 2 occurs, and I get that this bit generates a group isomorphic to Z2 to the K, then the only problematic edge is this one, the UW1 edge. And now what I'll do is I'll apply this stronger hypothesis that I can move the parity around to any edge. I'll apply that hypothesis to one of these edges, which still remains in this graph. And so it tells me that through one of these edges incident to U, I can find my nice collection of X circuits. And now whenever I go back over here, this tells me that I have to look something like this, where this is my circuit C, this one now, right? So I have to hit it twice. And the second time I hit it, I've now contained the edge UW1, and I can use this fact to move the parity around. So I know that that's not entirely clear, and there's like some trivial cases that can happen where maybe it looks a bit more like this instead with the 2 funny years, but the point is that you can use this stronger hypothesis to maintain the hypothesis all around and re-sign this this new edge that you didn't understand. So we've covered at least the most important bits of this proof for the case whenever the flooding number is equal to 0. But now let me say in general what happens. Why might the flooding number be small instead of equal to 0? So given our discussion before, one really obvious reason is that maybe there's just a small number of non-zero edges. And I like drawing this picture where these little squiggly edges are my non-zero edges, right? So maybe there's just 2 non-zero edges. Maybe that occurs after shifting. That's not so interesting, but the second outcome is more interesting. And that is if I take a set of vertices which contains V and juices apart with few non-zero edges, as long as there's few other edges, few edges in the boundary, then I still can't have many edge disjoint non-zero circuits that begin and end at V. Right? Okay, so I know our definitions are all a little long here, right? But I'm asking, remember that the flooding number is the maximum number of non-zero circuits in a collection of circuits that begin and end at V and partition yard set. So let me look at what those circuits can look like. Where can they pick up their non-zero-ness? They can either use an edge with both ends in this set, or they can use at least two edges from the boundary because they go out and pick up their pairing. And so the point is that no matter what, if I call this set A, now I have an upper bound, which is this number of non-zero edges with both ends in A. I'll write that like that. That's the number of curly arcs, the number of non-zero arcs with both ends in A, plus the size of the boundary over 2. Now, so this is my upper bound. And Janowski, Gielan, Godin, Gerards, Godin, Lowen, and Seymour proved that if you don't require every edge to be in one of the circuits, if you just have a collection of edge disjoint circuits, then this is tight. And so our theorem will be similar to theirs, but say that we actually care about the group a bit. And so it's easiest, I think, for me to write this by putting up their theorem rather formally on the board first to see what the differences are.
Theorems holds for in the group.
Yes. The group doesn't actually appear in the min-max theorem at all, which is, I think, kind of interesting, but it holds for any group.
Not necessarily abelian, isn't it?
Right, yes. And again, it's written additively in that paper, but so the theorem tells you that the maximum number of non-zero circuits in a collection of edge disjoint B circuits is equal to the minimum of this thing over all shiftings and all sets of vertices A that contain B. And I should say that their theorem is not stated this way, and it's not immediately obvious how to get this from their theorem. Their theorem is a collection of, is about a collection of vertex disjoint paths with both ends in a specified set. But if you do a construction that's similar, looking at a line graph where you subdivide everything once, and then this is what you get. So this is actually a corollary of their theorem. And this observation about the connection is due to Ross Churchley. So it's written in his thesis for sign graphs, and we believe that the same construction works for general groups. So I said yes with a lot of confidence, but I'm realizing that it's by going through this construction, and so I should give a little note there. That's the number 1, 0. Circuits. Collection of S disjoint B circuits. Equal to minimum over all sets A of vertices that contain B and all shiftings gamma prime of gamma. Right, so here's B, here's my set A. I'm working with respect to some shifting. It's equal to the number of non-zero edges of both ends in A. This fits. Plus the boundary of A over 2. Okay, and the other thing about this is that I'm writing a simpler version of the theorem for Eulerian graphs. But you can see by applying their theorem to the subdivided line graph construction, you'll get something, and that'll be a characterization in general. Okay, so we know that this isn't the right answer for our setting where we want these circuits to partition the edge sets. We know this because of the two edge cuts example, but let me give another example. So what happens for four edge connected graphs? I think it's a natural question to ask if these two edge cuts are the only problem. So this equality holds for the flooding number for graphs with no two edge cuts, and those are called four edge connected graphs. So you might already expect from the way I worded this that the answer is no, but let me write out an actual example of what can happen. So it's one particular graph with four vertices. This is the vertex V. For each of these digons, one has weight 0 and the other has weight 1, and it's over the group C2. And then this top arc has weight 1, and these guys have weight 0. So what's going on? I have a collection of 3 edge disjoints V circuits, these 3. But anytime I try and add the rest to one of those circuits, it changes its parity and makes it a 0 circuit. And there's no way of getting around this. So we know a nice way of seeing that there's no way of getting around this is that anytime your group is isomorphic to V2, the number of non-zero arcs has to be equivalent to the flooding number mod 2. Right, because if I can write my graph as a sum of some V circuits, then since these partition the arc set, the sum of the number that's non-zero is equal to the sum of all the arcs, right? So this, the number of non-zero arcs here is equivalent to the sum of all the arcs, yeah, and that's equivalent to the flooding number. So indeed, for this graph, there's 4 non-zero arcs, but the degree of V over 2 is just 3, and the parity of those is difference. Yeah, so what I'm saying is that this statement here shows that the flooding number of this graph is equivalent to 0 mod 2, and that means that it has to be less than 3, because that's right. So I know here that there's a collection of 3 disjoint non-zero circuits, but the flooding number has to be less than 3 because of parity reasons. And this is almost all that can go wrong now. So we've seen with 2 edge cuts that there's only one way of going through a 2 edge cut. And it turns out that the same thing holds for bridges of G fleet V. So what's going on is that I can combine 2 examples that look like this along a bridge. So in this example, the graph is going to be V2 to the 2 labels. On each side, it looks like that. But then they're glued along the bridge. Yeah, so this would be 0, 0, and 1, 0. 0, 0, 1, 0. And then with the other generator, I'll have the same thing over here. And then on the bridge, I'll sum up what the 2 arcs would have been labeled. Right, so the point is that if I forget about, I can imagine cutting this bridge in half. I have one part which is labeled 1, 0, and one part which is labeled 0, 1. And now if I forget about the right-hand side, I get that picture, the one from before. And likewise, if I forget about the left-hand side, I get the same picture as before. Okay, so now I can state what the actual theorem is, at least a little informally. And I know that stating the theorem by the end of the talk is a pretty low bar to try and reach. But as you can see, there's quite a few things that can go wrong in different places where the group can show up. So I've already stated what happens with two edge cuts. So I'm going to state the theorem for a 4-edge connected graph, just so I don't have to deal with it again. But it really is a precise theorem because you can deal with the 2-edge cuts that we saw before. So for a 4-edge connected graph, the flooding number is again equal to the minimum over all sets A that contain B and all shiftings, gamma prime of gamma. The first bit is the same. I still have some non-zero arcs with both ends in A, and those have to count. The next bit is also the same. It counts 1/2 for each arc of the boundary. But now the flooding number is harder. It's harder to get a flooding, to get this collection that partitions the arc set than it is to get an edge disjoint collection. So now I'm going to need to subtract something to get rid of a little bit. I'm going to subtract 1 for each so-called odd components of G delete A. So the point is that some of these components might decompose along bridges into parts which each look like that first example at the top right. So I'll say it out loud what the definition is, but it's a technical state. So a component of G delete A is odd if I can subdivide its bridges and put a label on each side in the appropriate way, so that for each block there exists an element of order 2, so that every arc with an end in that block is either 0 or has that weight. And also the sum of the number that's non-zero is wrong, is different from the number of boundary edges over 2. So that's a mouthful, but the point is that if you just subtract 1 for each component that looks like what we've seen, then you get something that's tight. And I wanted to say one thing about the proof, which is that the hardest part is figuring out how to shift these components. And again, it's similar to how we approached the 2-edge cuts, in that we essentially work with ear decompositions that begin with a certain circuit in here. And it's much more complicated in the 2-edge cuts case, but the idea is really the same. I mean, you can see the fundamental points there and how we would find the shifting. Right, thank you.